it Bridget? Okay. All right. All right. Let's get going from the current slide. And let me go over these announcements. I think you've heard them ad nauseum, but just in case you may have missed them. Coming up, 1 week from tomorrow, is the Lawson State Community College Transfer Fair Day 2020. This will be on the Birmingham West Campus Academic Building, that's the B Hall, from 9:30 to 11:30, Wednesday, February 12th. Then the next day, that's a week from the day after tomorrow, the February 13th, it'll be 9:30 to 11:30 here on this campus, in this building, somewhere near the cafeteria, okay? They say in the college cafeteria, but that's sort of a small space, and there'll be ending breakfast and beginning lunch right about that same time period. I just can't imagine them getting all the tables in that one little space while people are trying to finish breakfast and eat lunch. So I think they'll be next door in the faculty staff dining area, which no faculty and staff uses that I know of. So I think they'll probably be there and in the maybe in the hallway outside there. But here, some of the colleges have been invited. You're certainly welcome to take a look, and please plan to go by and at least chat with some of them just to see the types of things they are interested in finding out about people who may be coming to study there. And if any of you, either yourself or know of someone interested in the fields of mechanical, electrical, or material engineering, there is a great research experience for undergraduates being offered at University of Illinois, University of Arkansas, and Howard University. 10-week internship, exposure, all kinds of really neat stuff in academic research. And to get this really highly beneficial experience, you don't pay a dime. They pay you $5,000 for you to go and participate. They also give you free housing at the same time, which usually includes food. Usually the housing vouchers include the cafeteria passes, and they pay airfare there and back once, 1 mile round trip. If you're interested in this, I've got more information here. You're certainly welcome to look, share it with others. I've got a brochure here. The deadline, I think they said on here, was February 15th. That's a Saturday. That's a weird day for a deadline. On the brochure, they said February 17th, which is more likely because that's a Monday. But there it is. Please take advantage of it. Share with friends, anyone who may be interested in those areas. All right, before we get started today, we're in 18.2, going to start talking about seismic waves. Remember what we were talking about before was evidence of Earth's internal structure, and one of these evidences were seismic waves. So we're going to be beginning right there talking about seismic waves. Now, before we get started on that, this is chapter 18. Remember last time we finished chapter 17 and finished the lab for 17. So if any of you do need that lab, I've got it. 1, 2. Any others? This is a computer lab, and if you listen to the YouTube video, you will see and hear most of what you need to do the lab. So if you have a laptop or access to any kind of computer, you can do this. I'm sorry. You can do it on the phone. On the phone too, yeah. This is the lab we did. Anyone else need a copy of the last lab? Oh, good. Thank you. Okay. So we finished the chapter and did the lab, which means today we are scheduled for the test on chapter 17. That'll be the last 30 minutes today, starting at 5:15. So don't let me go past 5:15 before we start on that. Now, so we're here near the beginning of chapter 18. If we can finish this in the first 2 hours, which I don't think we'll be able to do, then we can have the lab for today. I've got it run off. But even if we go more than that, the lab today is very short, or at least the part that we'll do in lab. The second half, because this is a very short lab they gave, so to get enough points for your 25 points, there's going to be answering some of the questions from the book. This is one of the few labs that'll be the case. In fact, I think the only lab, but because it's so short. It's a good lab, but it's just real short. So we will do the lab, and then because the rest of the lab is answering questions, it's sort of like the moon lab. You've got to do that basically on your own time. And I did get the first moon lab in today, so that's good. But if you, we could actually maybe squeeze the lab in. If you don't want to hear me start talking about chapter 19. We'll see. See how far we get and whether we want to try to squeeze the lab in or not. So, any questions on anything we've covered up till now? Hopefully you have been working on or have your step formula and equation sheet for chapter 17 ready, because that'll be the last 30 minutes today. If you don't, you have some time to work on that. So let's talk about, if there's no questions, about what we mean by our seismic waves. Basically, these are waves that happen because of earthquakes. Now, it's not unique to earthquakes. Because there's so much energy in atomic explosions, whenever anybody, they shouldn't be testing atomic weapons. There's test ban treaties for this. But if anyone does, everybody's seismographs goes off, okay, or not, or a lot of people's will, and they'll know, and they can tell the difference between that. But basically, these are for earthquakes. Now, earthquake usually happens, we'll be talking about this later, pretty far deep into the Earth's structure, okay? That's where the earthquake actually happens. The waves, the vibrations from that, move all around the globe, okay? There are three types of waves that come out of this. The first is called the P wave. Now that P you can use to stand for a couple of words. First is pressure wave, from compressional or longitudinal wave. I'm going to explain that to you in just a minute. Do we lose somebody or gain somebody? Oh, okay. Okay. I was thinking someone was coming in, they never did. So that's one way. Another way you can think of a P wave is a primary wave, meaning first to get there because it's fastest. Okay? So the P wave, you can think of it as a pressure wave or a primary wave, meaning the first one to get there, first. Okay? Now here's the deal with a P wave, a pressure wave. Have any of you ever experienced a pressure wave? You are experiencing one right now, if you're listening to what I say, because sound is a pressure wave. I am speaking, somehow the larynx and other things are adjusting the air that's leaving my mouth, and that compression and rarefactions of the air that hit your eardrum, and that's what enables you to hear. We are amazing machines to be able to pick up on that. But if you hold your hand in front of your mouth while you're speaking, you can feel those little pulses of air going in. That's a pressure wave. Now, why is it called longitudinal? That's because the wave itself is going in this direction, and the propagation of the wave is going in that direction. In other words, the vibrations are this way, but so is propagation that way. Okay? So that's called longitudinal. It's in the same direction of the disturbances, you might call it. Okay? They're also the fastest of the waves. But here's the other thing. P waves, pressure waves, move through solid materials. if you think back of the old cowboy and western, or the cowboys and Indians, or the bank robbers and whatever, the train robbers, how did they know the train was coming? They put their ears down to the track, and they could hear the train coming way further off than they could through the air, because sound and P waves go through solids as well as through gases. But not only that, they go through liquids as well. Okay? Solids, liquids, and gases. The primary, the P waves, the pressure waves go through all three. Okay? That's going to be important in just a few minutes. You'll see why this is so important. It goes through liquids. Now, the S waves. There are a couple ways you can remember S waves. First, they're shear waves. And shear means transverse. And here is my classic example of this. I can remember when I was a little boy, it didn't take much to entertain me, obviously, because when we were doing something and had a hose strung out across the yard, I like to go and pick up one end of the hose and raise it just as high as I can and bring it down, and then watch it snake down the yard. Okay? What had I just created? A shear wave, a transverse wave. Now here's why it's transverse. I went up and down with my motion, but the wave went that way. So they're perpendicular to each other. Longitudinal waves are in the same direction. Okay, the disturbance is in the same direction as the propagation. The shear wave, the transverse wave, the motion is up and down, but the wave travels that way. The wave front moves that way. That's a shear or transverse wave. The other, secondary, primary, secondary, second fastest wave. Not quite as fast as a pressure wave, a P wave, a longitudinal wave. And here is the key for that. Because a pressure wave, a liquid will pressurize and transmit perfectly fine. If you've ever been in a swimming pool underwater and you hear things, you hear them fairly clearly under there, okay? Whereas if you try to do this with water, you can't do it because water only transmits in the same direction. It doesn't transmit vertically. So S waves, shear waves, transverse waves do not travel through liquids. That's going to be important later on. Just about as important as Eric getting here. Okay. Good deal. Okay. Now, so there's the second primary waves, secondary waves, second fastest. Okay. The third type of wave is the up and down, crest and trough wave. You can think of this as a water wave. Okay. And this is a surface wave. Remember I said the earthquake happens somewhere down here. Okay. And wherever the wave's being transmitted, through the earth or through, coming up or wherever, when it does reach the surface, then it creates tremors this way. Those are the surface waves. Much like water waves, those are the slowest of these three. Okay? And they occur where either S or P waves reach the surface. So when that primary wave reaches the surface of being somewhere deep in the earth, then it creates a surface wave. When the S wave comes along a little bit later, it creates a surface wave. These are what we're measuring with our seismographs. They're measuring the surface waves, but they are also detecting the S and P waves as well. Okay. Here are some other examples of these two. The primary wave, now I've never seen a spring that can, you hold out like this and it stays perfectly straight. It's going to sag. But the general idea is this. If I were to take, that spring was really stiff and it stayed straight like this, and I push on the spring and pull back, then this compression, when I push, it creates a compression. Then when I pull back, that's called a rarefaction. Okay? Well, once you do that, then now they haven't drawn it well here. This should be a compression here, the rarefaction there, compression here, rarefaction there. It's moving in the same direction of the wave propagation. The particle motion back and forth is moving in the same direction as the wave propagation. And this is Asia, right? Okay. We're basically in 18.2 seismic waves. Figure there, figure 18.2 on that page. Whereas the shear waves, the transverse waves, are up and down motion. The particle motion is up and down like my hose on the ground. He's doing a tight talk string, does this, and you see the wave propagation is perpendicular to the particle motion. And also Justin. Parallel to Justin. Okay, hold on. All right. Any questions on the seismic waves? Now you might ask yourself, oh, this is interesting sounding, but what difference does this make to the structure of the Earth? Plate tectonics, for instance. Okay? Well, we're not there yet. Okay? Let's do this part, and then we'll tie these last three things sort of together. The Earth's internal structure, three main zones. Okay? The first of these is the crust. And the crust is the very smallest. It's where we live. It's basically where we mine. It's probably everything we ever do is within the crust of the Earth. No matter how deep we think we've dug, we're still probably in the crust. Okay? I think this next slide, I should have gotten it up before you took your picture. The crust is this really thin little brownish strip around here. It looks incredibly thin, and it is. It's just several miles thick, and that's all. When you consider how huge the Earth is, that's nothing, okay? But we never get anywhere beyond that, pretty much. That's the crust. The very smallest. Say again?
I suppose we get in is the crust.
Yeah, the very seldom have we gotten into anything below the crust. Okay? Occasionally we do. I think the Russians really put a big effort into getting down into the mantle, and I think they got there. Okay? Now, the next part is the mantle. Much thicker than the crust. I mean, much, much thicker than the crust. Now, actually, the mantle is the tan part here and the browner part, the in between tan and brown. The brown is the crust. This is the upper mantle and the lower mantle. Way thicker than the crust is. Way more massive than the crust is. Okay? And then you get to the central part, and that's the core. The core is also made up of two parts. This was upper mantle and lower mantle. The core is made out of outer core and inner core. Okay? And you might say, very reasonably so, look, if we've never been past the crust, and we typically haven't, how do we know this stuff is there? Okay? And that's what we're talking about. That's why we brought up the thing of the waves. That's why we brought up a lot of what we talked about last time and going into this time. No one's been down there. No one could go down there, okay? It gets incredibly hot. Yeah, it's still in the mantle, you're incredibly hot. And when you get here, this is molten rock down here. I mean, it's melting, okay? You couldn't possibly do that. So Hollywood, Journey to the Center of the Earth, strictly Hollywood. Nobody is even going to come close to that, okay? So there's the basic structure. At least that's what we think it is. No one's been there to tell. So how in the world do we know? Well, let's talk a little bit about the things we do know. The crust covers the Earth, the entire Earth. There is a thin, maybe a few miles thick layer, and that's everywhere. Two types of crust, though. You have the oceanic crust, which is the crust that's underneath the oceans, And then you have the continental crust, which is underneath the continents, okay, which is the continents, basically, okay? The oceanic crust is much thinner than the continental crust, okay? It's also a different rock, basaltic rock. Remember the black rock, the pieces that I had from doing our bathroom, master bath at home? That was the basaltic crust. Usually very dark, meaning high iron content, but also very fine crystal size because it cooled very quickly. Okay? All this ties to what we did last time. Okay? It's much denser because of the high iron content. Okay? That underlies much of the ocean. Then the continental crust is made mostly of granite rock, not basaltic. Granite, remember, is a lighter color, lighter weight, less density, very little iron in it, so that's why it's lighter color, and less density, less iron in it, and made up mostly of siliceous material, though it does have other materials in it too. Large crystal size, so meaning it formed usually deep in the earth, slowly making large crystal size. Whereas the basaltic rock under the ocean, well, that's when volcanic eruptions happen there, it cools really quickly, so it has finer crystal size. Now, between the crust and the mantle, which comes next, is this thing, I don't even know how to pronounce it. I call it the Mohorovičić discontinuity. And to shorten it, they just call it the MOVO. Okay, the book calls it the MOVO. Okay, it's a discontinuity. That's the boundary between the crust on top and the mantle underneath. Now, how we know that's there? The seismic wave velocity increases sharply when you go from crust to mantle. And to me, that's totally backward, because the seismic waves are usually coming from deep up this way, so it should be the seismic wave velocity decreases sharply going from mantle to crust. That makes a lot more sense, because you think of them as coming this way rather than going the other way. But the same principle, this discontinuity, you can tell when it hits, okay? You can tell the seismic wave velocity changes pretty sharply, okay? Now, this is the illustration of what we're talking about here. Underneath the ocean, the oceanic crust, very dark, fine-grained, basaltic, dense basaltic rock under there. There's something I don't like about this drawing, too. I'll tell you in just a minute. And then you have the continental crust, which is much thicker but much less dense. This is usually granitic rock, granite. You know, low iron content, large crystal size typically, and this is under the continents. Okay? And then somewhere underneath all of, yeah, was there a question? Somewhere underneath the oceanic crust and the continental crust is the mantle. Now this is shown as if it's really thin. You know, everything's thin. No, this is pretty thick before you get to that. But this would be the Mohorovičić discontinuity between the crust and mantle, whether it's the oceanic crust or the continental crust. Mantle is under. What does it do?
Yes.
It's just a discontinuity. It's just like if I were digging in my backyard, which I have done before, and suddenly hit a layer that's just about rock, okay? That would be thin soil, loose soil on top, and suddenly maybe a clay layer. That would be, and that boundary of that would be the discontinuity, okay? It went from being workable to not workable, you know, that's what it is, just a discontinuity in density and everything else, okay? If you remember back in the last chapter when we talked about some of the minerals in the oceanic crust, and that's the basaltic rock, and the basaltic rock has lots of biotite in it, a little bit of biotite in here. When you get into the mantle, you have the olivines and the augite and those other high iron content, very dense, much denser than even the iron content of the basalts, certainly than the granites. And what this is showing that if you have an equal volume of these two, because this is denser, this weighs a lot more. And that is basically going to be part of the lab for this chapter, is the density between basalt and granite.
And you did say that we've been to the mantle, right?
That what?
Science has been to the mantle yet? Science
They
has been
have
to the
been.
mantle. Yeah, I'm asking.
There are some places, I'm pretty sure, that the mantle comes pretty close to the surface, and we probably have dug into the mantle. I think
But that's floating rock. That's liquid rock, isn't it? The mantle?
yeah, the mantle is, especially what you see here, would be very dense rock. Okay? Now, I think what you're getting at is coming up really soon. You have some issues in the mantle. That's why there's an upper mantle and a lower mantle. And we'll talk about that as well. Coming up really soon at a station near you. Okay? So let's talk about the mantle. It's a very thick shell. The crust, incredibly thin. The mantle, a very thick shell between the crust and the core. Now catch this. How thick is it? Takes up 80% of the Earth's volume. Okay? 80% of the Earth's volume. That means at most the core is going to be 20% or less, and the crust is going to be almost negligible. Okay? So it takes up so much of the volume, it still accounts for only 2/3 of the Earth's mass, which is by far the most of the Earth's mass as well. But this is 67%, that's 80%. Well, that's because the core is so much denser than the mantle. And the mantle is so much denser than the crust. So you have density increasing as you go down. So 2/3 of the Earth's mass, 80% of the volume, that's in the mantle. And as I was saying, composed mainly of olivine, which is a ferromagnesium silicate. One of those. Remember, we broke up our silicates into ferromagnesium and non-ferromagnesium silicates. This is heavily iron with magnesium. Okay? Now, what we do know about the mantle, even though, except for very few circumstances where we have gotten into it, very little, here's what we do know. From our seismological data, which we're going to be talking about soon, that gives us some indication of the mantle, its thickness, its volume, its mass. We found out that. Now this is the one that on first reading made no sense whatsoever. Data sources from the mantle, which is deep in the earth, the nature of meteorites, which are flying around in the sky. What? How does the nature of meteorites have anything to do with what's inside the earth? Well, guess what? They probably are made out of the same materials because they were made about the same time. Okay? So, we'll get to that later. And this is the one that we really know about, the materials that are ejected on volcanoes. That's the stuff from the mantle that comes up. Okay? Now, I guess I always pretty much assumed that what came out of volcanoes was molten rock, liquid rock, right? That's what you always see. But that's not always the case. Sometimes chunks of solid rock get blown out of there as well. And certainly lots of gases spew out of there. So you have all sorts of stuff coming out of there. And most of what's coming out of there is deeper than the crust. You're into mantle material. So by studying the materials ejected from the volcanoes, both the chunks of rock that come up and the molten materials, we have more information about what the mantle is like. Now, what in the world does this mean? Basalt correlation. Okay? And I don't know why they use basalt here. What they're doing is going back to this meteorite thing. But I guess it is that. Now, we're talking about the mantle and going to talk about basalt, but basalts are in the ocean crust. So it's a little bizarre, except the basalts come from, volcanic material too. So that's where the correlation sits. They don't do a great job of explaining it, but they're talking about it. The basalts are close to the silicate chemical composition of stony meteorites. Remember, we had several kinds of meteorites. One was rocky or stony, and the other was stony iron, I believe they called it. The basalt is close to the chemical composition of the stony meteorites, and I believe by inference then, the mantle material would be more like the stony iron meteorites. Okay, that's a stretch. But this is the most common volcanic rock, the stuff coming out of the volcanoes. That's going to be close to what we see in it's what we can measure coming from the mantle, because that's our best source of it, and it relates to those stony meteorites. Strange but true. Okay? People still writing or? Okay. Move on. Okay? So now we get down to the core. Okay. The core makes up 15% of the Earth's volume. Okay, 15% of the Earth's volume. What did the mantle make up? You remember? 80. That left how much for the crust? 5%. That crust that goes all over the Earth only makes up 5% of the Earth's volume. Okay? The core makes up a third of the Earth's mass. What did the mantle make up? The mantle made up 2/3. That left the crust being negligible. Okay? The crust is so thin, even though it makes up 5% of the volume, it's so low density, just about all the mass is in the core and the mantle, mostly in the mantle. Okay. Now, how do we know anything about the core if we can't get down there to measure it? Well, from that P-wave seismological data. This is telling us a lot. Okay? Now, I'm going to show you the figure because it's hard to talk about this without the figure. Okay? What was characteristic of the P waves, the primary waves? Say again? The fastest, yes? What else? They go through liquids as well as solid. Okay. So when they're measuring P waves, okay, let's say an earthquake happened here, okay? Then all along here through the mantle, those P waves are being transmitted. And we have seismographs all over the Earth, internationally. All the countries agree to run the same type of equipment, share the data, everything. Everybody knows when there's an earthquake anywhere, okay? So there's the earthquake. It transmits through the mantle. But when it reaches the core is, the outer part we think is liquid. Now, I think they don't quite have the dimensions right here, but they're pretty close, I bet. And when it goes from the mantle to the core, you notice the waves get diffracted because there's another interface. They don't have a name for this one, not one that the book talks about. Just like the Mover-Rovichik discontinuity, there's another discontinuity between the solid mantle and the liquid core, outer core. Okay? So you see the waves get bent a little bit there. But then when they get down here, they get really concentrated, And when they leave here, they spread out again. So they're spread out, concentrated, spread out. That accounts for the solid core. No other model will fit why the waves get closer together here. Now, how do we know they get closer together? Because here you see the P waves transmitted here, but when they hit this discontinuity here between the solid mantle, the liquid core, there's a shadow zone. A shadow zone. No P waves are detected here. Remember, we've got seismographs all over the Earth, but there's a shadow zone between 103 degrees from the earthquake down to 142 degrees. There's a 39 degree range there. No matter where the earthquake is, there's always the ring, you might say, that there's no detectable P waves. Well, maybe they just got too weak. No, they didn't. Because here you start picking them up again between 142 and 180 degrees. They go through here. And what could cause this? The fact that there is a discontinuity between the mantle and the liquid core, and then there's a solid core that concentrates and spreads out again. It's the only thing that can model and tell us this. Without this information, we wouldn't have a clue. Okay? But we do have this information, and it's pretty incredible what we can learn just from those P waves. They do transmit through, but there's a shadow zone here, meaning there's got to be a discontinuity here, which would be described between a solid, liquid, and then a solid again. That would create the spread. Okay? So the P waves are refracted, means bent, by the core that produces the shadow zone. If we were solid mantle all the way through, the P waves would come through all the way through. There has to be some reason the shadow zone's there. That's because it's a liquid core. Okay? No direct P waves seen between 103 and 142 degrees from the earthquake. Now, because of the size of that and the modeling they've done, they can calculate the shape and the size of that outer core and the inner core. The source of the data on the interior, this is the primary source of the data on the interior of makeup of that core. The fact that the waves seem like they compress here and then spread out again, that indicates there has to be another discontinuity in here that's going from liquid to solid back to liquid again as you pass through. Okay. But the P waves do it. They pass through. All right. Well, how do we know it's not just different densities of solid? Why would we even think that there may be liquid in there? Well, let's continue with the core. The S waves. Guess what? The S waves are what kind? What does S stand for? Secondary, meaning second fastest. What's the other S word? Second? Shear. Okay? Shear meaning the particle displacement is perpendicular to the wave transmission, the wavefront. And what do they not do? They will not go through liquid. And look at here for your S waves. They follow the same pattern here through the mantle material, the solid material, from the quake to 103 degrees on either direction. It's just a little slower, but they get there. Okay? But then their shadow zone is a complete shadow zone, meaning the outer part of this core has to be liquid. If that was solid rock, S waves would go through it. They do not penetrate at all. That means the outer part of the core must be liquid, but the fact that they get bent like this means the inner part has to be solid again. But the S waves can't make it there because they can't go through the liquid part. Okay. So it's pretty incredible what we can learn just from our seismological data. Okay? It's a larger S-wave shadow zone. The entire, anything on the Opposite side of the core, not going to have an S-wave on it, meaning the outer part of the core has to be liquid. Okay? The core acts like a liquid, not allowing S-wave propagation. The core has two parts, the liquid outer core and the solid inner core. That's supported by the combination of the S waves that tells us the liquid on the outside and the P waves that the model has to get closer and then spread. Only way they can account for that second part that breaks the shadow zone for the P waves. Okay? So that's how we know without ever going down there. Now, other core evidence. And again, this seems nuts to me that core evidence is in iron meteorites. Okay? Whoa, okay? Now, the iron meteorites, we talked about the stony meteorites. The iron meteorites are mostly iron or an iron-nickel alloy. Okay? Now, they're thought to mimic the chemical composition of the core. Thought to because we can't take a sample of the core. It's way too hot. But they were formed similarly, so we think they probably do mimic this. The stony meteorites, more like the basaltic correlation, the mantle type stuff. The iron meteorites, more like the core. Okay? Now, the other feature is the Earth's magnetic field. Now, if you had had the first part of the book, you would know the only way a magnetic field is formed is from a moving charge. So therefore, since the Earth has a relatively strong magnetic field, there have to be charges moving. Well, the only motion the Earth has is its spin, pretty much. And the fact that a solid, okay, do you mind if I'm not going to do anything else there. If you had something in here you could see, and I spin this, the liquid doesn't necessarily spin with the outlet, right? It sort of stays the same. If you had, say, a peanut or something floating on there, I could do that, and the peanut would move much. Okay, they can jiggle because I jiggle it. But you see, when the Earth spins, the liquid kind of stays the same, but the mantle, the solid part, has to spin with the Earth. So that's rubbing against it, and we're spinning constantly. Yes.
So you need to tell me the mantle is not a liquid but a solid?
Say that one more time.
You need to tell me the mantle is not a liquid but a solid?
Yeah, the mantle is mostly solid. I put in that mostly for a reason. We'll get to that later. Mostly solid. The outer core of the Earth is almost totally liquid, molten rock. Okay? Now, because the mantle is spinning and the core probably isn't, but it's made up of iron and nickel, which are both magnetic materials. There's only three naturally occurring magnetic materials: iron, nickel, and cobalt. We just don't have that much cobalt, so that doesn't enter the picture here as much at all. But because those are in there, most of the inner core of the core is iron and nickel. When it spins, it's knocking off electrons, getting them to flow, and the movement of charge creates a magnetic field. No other explanation can come up with why we have such a magnetic field. We have to have that interface. The source is a turbulent flow within the liquid core. Those charges moving in the liquid core. The material must conduct electricity. Iron is a great conductor. Nickel's a pretty good conductor. And it's also magnetic. It all sort of fits. Okay? The meteorite and the magnetic field data are consistent with an iron core. An iron core that's liquid on the outside, solid on the inside. And the liquid part bumps against a mostly iron mantle. Okay? So it all kind of fits together in the models and explains why we see what we see and how it all fits together. Okay? Everybody got this, or you need some more time? Okay? So, let's get a little more detail, especially in that mantle part. Okay? As if we haven't had enough layers already. Now, remember what we have? We have continent and oceans. The continent is made out of the continental crust, which is mostly what kind of rock? The continental crust. Granite. Underneath the ocean, you have the oceanic crust, which is mostly basalt, which is higher iron content. It's a thinner crust, but a denser crust. Oh, I'm sorry, I know you're taking a picture. As soon as you get the picture, I wanted to flash back in time. Remember I said I didn't like this picture. And here's why I don't like this picture. It doesn't fit with what we're going to see later. This is just an artist's drawing. But because the denser oceanic crust would tend to go under the continental crust. The continental crust would not be under this. This would tend to be under that because this is denser. So the continental crust usually sits on top of this, and this is being pushed under. We'll see that later, but that's the thing I meant to say why I didn't like that picture. That's it. It shows the oceanic crust on top of the continental, which probably isn't happening. Okay? We'll see that later too. So let's go back to where we were. Whoops. That's where we were. Okay? So what we had before was the two crusts here, and underneath the boundary of that crust is the moho. Okay? The moho. Underneath that is the uppermost part of the mantle. I can't read what it says. I think it's uppermost. Oh, let me hit some of this. Table 18.1. I should have hit this beforehand. Comparison of the oceanic and continental crust. The oceanic crust, they think, is basically less than 200 million years old, whereas the continental crust up to 3.8 billion years old. Okay? So quite a difference in age. And remember that rock we saw, the nice rock that had all the, it was a metamorphic rock, but become a sedimentary rock, and the layers had all gotten bent. And it was about 3.8 billion years old. So that was one of the earliest rocks that we think the continental crust had. The thickness of the oceanic crust, 3 to 5 miles. Okay? Sounds deep, but it's not. The continental crust, 6 to 47 miles. No, we haven't drilled anything close to 47 miles, or even close to 6 miles down, okay? Maybe the Russians did some, I don't know. The density, oceanic crust about 3, continental crust about 2.7. We'll see that in lab, whether it's today or next time, we'll do that. The composition, oceanic crust, mostly basalt. The continental crust, mostly granite, though you have some schist, some nice rock. Or we have some limestone too, which is a, what is limestone, by the way? It's what? Sedimentary, and what kind of sedimentary? Not clastic, chemical. The clastic is particle. And with that, I think David came in. Okay. Anyone else who I haven't acknowledged you, meaning I probably didn't catch you when you came in. Okay. All right. I meant to point that out to you because we will be doing part of that in lab. Okay, there are some examples here. Frankly, it's just playing games, you know, and having you do some calculations just to have you do calculations. I'm not going to mess with the first one there, except to say what is the height at which the oceanic crust floats in the mantle. They say about 0.6 of a kilometer. I'm not even absolutely certain what they're asking about there, but we'll let that go. What is the height at which the continental crust floats in the mantle? And that would be about 6.3 kilometers or 5.7 kilometers. So I mean, it is some information there that's sort of useful, but it's not that much. Okay. So we're looking basically at the figure that's on page 463. Now the one in your text is mostly the right hand one, not the left hand one. The left hand one is not as detailed as the one on the right, so they left off the other. All right, now, oceanic crust, continental crust. Here's the uppermost mantle. Underneath the uppermost mantle, there is a band or belt of materials there they call the asthenosphere. Weird sounding name. Sphere, of course, means spherical, okay? So it's a sphere. It's a thin, now they show this fairly thick. They probably exaggerated a little bit, maybe quite a bit. Thin, hot, elastic, semi-liquid layer in the uppermost mantle. So that's the asthenosphere there. And then you hit more mantle coming down here, which is solid again. Now, the reason we know that's there is distinguished by a sharp decrease in the seismic wave velocity as you're going from mantle to asthenosphere, because it's, now do you know what it means by elastic, semi-liquid? Do those words mean anything to you? Okay. Second? Okay. We usually think of elastic as something that stretches. The more proper way to think of it is something that returns to its original shape when it is stretched. Okay? That's what makes something elastic. That when you deform it, it bounces back. It comes back. Like throwing the ball against the wall. If you took a picture of that ball when it hit the wall, you see the ball flattens out against the wall, but then comes back spherical again. If you've ever seen pictures of people hitting a tennis ball with a tennis racket, the ball flattens out against the racket, and the flat racket actually bulges back, but then they both return to their original shape. That means they're elastic. If you've ever seen a picture of when they hit a golf ball, as hard as that golf ball is, it flattens against the head of that club and then bounces back. Yeah.
When it's in motion, does it stretches?
What's that?
When the tennis ball, golf ball, or whatever type of ball,
Right.
it's been compressed by an object and ejected from it. Does it somewhat stretches?
Is it what?
When it's in motion, does it somewhat stretch a little bit?
Maybe right at first, but you mean does it oscillate a little bit? It probably does a little. Okay. I have sort of a dumb illustration of elasticity. Has anyone ever played much volleyball? I bet you have sometime back in your past. Would you count a volleyball as hard or soft? It's softer than a golf ball for sure, but it's still pretty hard. It's about the same as a football or a basketball. It's pretty hard, maybe a little less, but it's really firm. That's a good way to put it. Well, when I was in University of Nebraska Lincoln, I was working on a graduate degree. A group of us got together a co-ed volleyball team. We had a couple of gals in our chapter who were, one was really tall, she had played in high school, and the other was a wonderful setter. They had played with each other, and they just knew, and we got the core of a good team here. The rest of us just filled in. Those were our secret weapons. Okay, so and we did okay until one afternoon we were playing some weekend. We had a match scheduled. We went out there, and this other team had a really tall gal with a really good setter. We went, okay, ours are good, but we watched them. Boy, she pounded that ball. Okay, and that gal could set it up for it perfectly. It looked like every time. And if you know how volleyball runs, the teams rotate differently, so you always, at some point, are against everybody else. I mean, right across the net from every other person. And sure enough, when it was my turn to be across the net, you knew what was going to happen, okay? So I was getting ready, and sure enough, we either served or returned and stuff, and they got it to their setter. The setter set it up perfectly to this really tall gal who could really spike that thing. All I could do was go up as high as I could and cover as much as possible to see if I could just knock it back across the net when it came. And all this stretching and getting up as high as I could, that ball came down in an enormous velocity right in my face. And it was not a soft volleyball, but I felt that ball hit both ears at the same time. It deformed, okay? I deformed it, and it bounced right back to its original shape. It was elastic. Unfortunately, it bounced back to its original shape on our side of the net, not on the other side. So not only did I get it, all I saw was Wilson, you know. That part I forget. Okay. But that was elastic. It returned to its original shape. Semi-liquid, which is sort of interesting, that elastic would be semi-liquid, but that's a layer in the upper mantle. Okay? Now, they don't ever come right out and say this, but my guess is this is the source of much of our magma that comes up in our volcanoes. There may be other pockets in the upper mantle or maybe even lower mantle, but I'm betting most of it is coming from there. Okay? Because it's semi-liquid, because it's still under a lot of pressure there, but if it finds a crack or a crevice or some sort of seam to go up, it goes up and reducing the pressure, it becomes more liquid. But could be carrying other rocks with it. So that's the asthenosphere. Now, remember when we talked about oh goodness, I can't think about it. It was the formation of basically sedimentary rock. I can't get the word to come out, but it had litho in it. And I said litho means rock. Okay, this is lithosphere, meaning a sphere of rock. Okay, the sphere of rock, the layer of rock, is the solid layer above the asthenosphere. What's that? That's the upper mantle, the crust, both crusts. Okay, that's the solid layer above the asthenosphere. Includes the entire crust, the moho discontinuity, and the upper part of the mantle. That's the lithosphere. That's where we get our rocks, basically. And it's made up of rigid plates floating in the upper mantle on this semi-liquid asthenosphere. This is the basis for plate tectonics. Plates are floating on that. Below this is pretty much a solid sphere. Above this, you got individual plates. And guess what? Where those plates come together, that's where volcanic activity tends to happen. And earthquake activity tends to happen. Not totally, but tending to that way. This is the whole basis for our plate tectonics. Okay, everybody got this one? That took way too long with the volleyball detail. So that's the theory of plate tectonics. Individual continents shift positions on the Earth's surface. There was a time people thought that was ludicrous. They can't happen. Continents are too big. They're fixed. But no, they do shift positions on the Earth's surface. The patterns between the continental shapes can be fit together. And this was the earliest observations that, look at this. South America looks like it could fit right up in there in the armpit of Africa. And this bulge in Africa looks like it could fit in the Caribbean and the Gulf of Mexico. Maybe a little big and tight, but it looks like it's there. notice how the eastern coast of North America angles out into the sea, where the western coast of Europe goes in the same direction. And you can almost imagine taking these and fitting them together and making one big, yes.
And that's why South America looks like Africa and Australia looks like Antarctica.
Somewhat, but Australia, if you think about it, they don't show this in a picture, but if you picture Australia curving up into the Atlantic Ocean, the Indian Ocean, it would almost fit. So it's pretty incredible. I didn't even see you come in. Kaya, right? Okay. I'm sorry, I can't.
I need you to sign right here.
What is this I'm signing?
The other half of this.
Oh, you're adding this. Okay.
Yes.
All right, good deal. Okay. Now, are they going up it? Because the last time I looked, it was full.
I dropped it. I was in
Oh, you were in it.
but
I
I
know you
dropped it. So I
Okay.
could just pay for 3 classes for my
Right.
tuition. And I tried to add it back today. But she said, go ahead and ask you since I was originally already.
Okay, and that'll probably let them open it. Okay. All right, let me get you here then. Since I assume you are. Okay, Kaya is here. Okay, has anyone else come in I didn't see? Oh, there was one I didn't. Okay. So, people had noticed this probably hundreds of years ago, and people had suggested it and got laughed out of the scientific community. You have got to be kidding me. Continents don't drift apart. That's ludicrous. It can't happen. Okay? It sure looks like the patterns could fit. And the original idea was we were all once a part of a single large landmass called Pangea. Now, the Gea here is sort of the same as you get in geology or geography, meaning the earth, solid earth material, pan meaning all one. Like a pandemic covers the whole earth.
Pronounce that word again.
Pangea, I think is how you.
Pangea. And that's the first before it spread apart.
That's what they called it. One big landmass. Okay? Now, that was a very good question. Where does Antarctica fit in? I don't know. Okay? Because it doesn't seem to fit as well, except that maybe it fits up in here somewhere, because see, this goes further down, and and Australia's over here. It could take it, so maybe somehow it does. Now, back when they first proposed it, they called it continental drift. And that's what people said. You're nuts. Continents can't drift. They're solid. How could it drift? Well, if they have that semi-liquid layer down there, yeah, they could float on that layer. And that's an interesting concept. And that's now what we call plate tectonics. Now, back to evidence again from the Earth's magnetic field. All right. Now they kind of left off out some stuff here. I'm going to try to fill in the gaps, literally. This slide seems out of place. Okay. And they're going to tell us this part now, and then later they're going to explain why. Okay? I wish they would have sort of done the why part first, and then this would have made more sense. Now, we know that volcanic activity has been happening for millennia. Okay? Long time before we were around, there was this volcanic activity. And there's still volcanic activity. And we're going to talk about some places where it's almost continuously going on. We just don't realize it, but it is. Okay? And what rocks are formed from volcanic activity? Igneous rock. Okay? And as these igneous rocks are laid down, the magma comes up and solidifies, they're laid down. When they are laid down, they reflect. Okay. This is all predicated by something that's rather bizarre, but true. The Earth's magnetic field, we think, comes from the moving charges of the turbulence inside the Earth, okay, in the liquid core. Okay? Now, here is the strange thing, and I cannot begin to explain why, but the evidence is there, irrefutably there, that the Earth's magnetic field has flip-flopped at least 22 times that we've been studying. They drill down through the rocks, and they see that sometimes the igneous rock record records the Earth's magnetic field strength and direction. Okay? Magnetite, which is iron ore that's naturally magnetic, the poles are locked into alignment with the Earth's field upon crystallization. When they crystallize, whatever the Earth's magnetic field was, it's just like when you take a pen or a needle that's not magnetic, rub it against a magnet, and it becomes magnetic. Okay? Well, same thing happens here. When you have strong magnetic field, the Earth's magnetic field lines, and then it solidifies magma in the direction of that, it's going to be magnetic because it lines up with the Earth's magnetic field. Now, I think there's a few things that are left out here, okay, but we'll talk about those. As they drill down into layers of magma, of iron ore, magnetite, they drill down, they found here, the magnetic field lines are going this way, and then suddenly they'll hit, not suddenly, but they will hit layers that the fields are pointing in the opposite direction. And then they'll hit another layer down here that points back in the first direction. And then that keeps happening. They have found 22 reversals over the past 4.5 million years. That's incredible. That's not that long since the Earth is about 3.8 billion years old. They have found 22 reversals over the past 4.5 million years. Okay? Now, they've detected these. They know they're there. Okay? And the reason is that magnetite locks into the strength of the Earth's magnetic field and points in that direction. And yet, it's varied, and here's the thing, strength and direction. Strength and direction. And here's what I think is sort of missing here. Some of these lines should be long, strong lines. Some of them are probably pretty weak. There may be even gaps in there when there's no field detectable. Okay? Now, here's the closest I can come to estimating what's going on here. I still can't tell you why, but this to me seems like a sine wave. Where here the field lines would be pointing this way, here they'd be pointing this way, here this way, and that could account for 22 reversals. A very slow oscillation in the Earth's core. And it could be because of the turbulent flow. The Earth spins in the same direction, but it could have a lag effect, and sometimes it's going one way and sometimes it's going another. I don't know. That's my best guess. But we know it's happened because they've taken these cores and they've detected 22 reversals over the past 4.5 million years. It's there in the rock. The evidence is there. Okay. So why bring up this geology here when we're talking about plate tectonics? Well, here's why. Evidence from the ocean. In the ocean, various places in the ocean, they found, let me go on and get the next slide for you too. They get these ridges and trenches. Okay? Now, one of these ridges is called the Mid-Atlantic Ridge and Rift Valley, okay? Now, if you'll notice, it bisects the Atlantic Ocean very closely to being exactly, okay? It goes sort of right down the middle of the Atlantic. Right between these places where the continents look like they could fit. In fact, it sort of looks like, doesn't it, that Greenland could almost fit in the Hudson Bay here. You know, it looks too big here, but that's because it's a Mercator projection, and you know it makes things that the poles look way too big. But it looks like these things could have gone together there, and they may have, or at least crunched together this way. Okay, maybe these things came from. I don't know. Okay, but we know this ridge is here, and one manifestation of that ridge is the whole nation of Iceland. That is a volcanic outcropping, you might say, from the Mid-Atlantic Ridge. The entire island, you know, there's more than one, of Iceland is volcanic, okay? And it's right on that Mid-Atlantic Ridge. Now, yes?
So you mean to tell us, along that mountain ridge in the Atlantic, there are volcanoes?
Okay, you're absolutely right. A previous edition for this book came with a set of CDs, but then they quit supporting them, so I can't use them anymore. But they actually had underwater cameras that showed lava bubbling up, and the camera was moving like this, bubbling up all along that ridge. Just, I don't know if it's constant, but it was happening. So basically, there is a splitting of the plates there. The Eurasian plates here, the North American plates here, the South American plates here, the African plates there, they are splitting apart and have been for at least 22 billion, 45 million years or something like that. Because they can measure and see that that's the weak zone. That's where it's splitting apart. Okay? These coincide with submarine, meaning beneath the surface of the ocean, earthquakes. Okay? The rift, this is really a lousy bullet point. Rift along crest. Okay? That means there is a ridge there. Well, they mean almost the same thing. That's where the break occurs. Okay? There is a large amount of heat escaping from the crest there. You can go over it with sensitive devices, and you can tell right when you cross it because they can measure the heat coming out of there. Okay? This is the Mid-Atlantic Ridge. And they say, and Rift Valley, because on either side of the ridge will be a Rift Valley. Okay?
How deep is that ridge?
What's that?
How deep is the Mid-Atlantic Ridge?
I don't know. It's pretty far down there. I'm trying to remember about where the Titanic went down. Was it somewhere right around in there? And you know how deep that was. And there probably are some, so it's way down there. But the ridge, and they can do sonar and stuff and tell right where the ridge is. Okay?
One question.
What's that?
One more question.
Yeah.
You think that's where, possibly where hurricanes get their heat from when they cross that ridge?
My concept of that is they're getting the heat from the sun. Yeah, because that's the surface phenomenon. Don't think it's coming from that far down. But I can't say no, because I don't know enough about it.
Ocean down to the floor.
Yeah. Well, the heat would be coming up from down there, but there's just so much ocean there, it's hard to imagine that big a concentration reaching one single spot. But I can't say no, because I haven't studied that. But it's an interesting concept. But I think it's mostly atmospheric, coming down right on the equator and heating up. Now, along with the oceanic ridges, there's oceanic trenches. Long, narrow, deep, deep troughs with very steep sides. They always run parallel to the continental edges. Okay. Not where you see here. Here are continents. If you've ever been in the Atlantic, you know, you can go way out, and the Gulf is the same way. You can go way out there and not be very deep, you know, and then suddenly hit a sandbar and you can be off. Yeah, we don't go deep. The West Coast, my word! If you look at sonar when you go out the San Francisco Bay, you don't quite see it here. The bottom, you know, in San Francisco Bay is not that deep. Go out here and then suddenly, I mean, it falls off, and then go a little further and it comes back up. That's the trench, oceanic trench. It's on this side. It's all along South America, Central America, North America. I bet you this side of Africa, I bet you that is. I think this is part of the trench here that broke off Madagascar. Okay? This is certainly a trench here. That's the Red Sea. It's a trench, okay? And on in the Pacific, you have more of it, okay? The ridge here, the trenches on the other side, okay? And we'll talk about why the trenches are trenches a little bit later, okay? I wish they tied them a little closer here. Okay, so here's the seafloor spreading hypothesis. The hot molten rock moves up from the Earth's interior, probably via asthenosphere. Let me get the picture here too. Yeah. Up from the Earth's interior as it emerges along a rift. Okay? The outflow in both directions creates new rocks. Okay? And the drilling evidence, as they drill down into the oceanic crust, the basalts that are down here, the thin sediment layers near the ridge become thicker the further out you come toward the continents. The older fossils are along the continents, and the younger fossils are all here, meaning there is no deposition here a long time ago, because this wasn't here a long time ago. So right along the center here, they're only 0 to 5 million years old. On the next ridge, side of the ridge, 5 to 23 million years. Then on the next side of that, this one and that one, they don't have the colors too good, they are 23 to 38 million years. And then here to here is 38 to 53 million years. Now that's as deep as we've gone to find, you know, those reversals. That was like 48 million years, but it's in that range. So haven't gone, of course, too deep here. But then the next ones are 53 to 65 million years, and then these real wide ones out here, 65 to 135 million years. Just by the fossils and other things, and you see you're getting right up to the shore there. But these are the oldest, meaning at one time they were probably together, these were together, these were together, and they have been slowly, literally drifting apart because the new magma comes up from the middle and spreads them further. C4 spreading hypothesis. Okay? The outflow is in both directions. The drilling evidence, the thin sediment, okay, we talked about that. The older fossils are here, and the newer ones, younger ones in the rest. Now, that's just part of it. That's fossils and those kinds of things. Layers, those kinds of things. But then we get, was everybody finished with that one? I didn't ask. Oh, sorry. I'll sit down and try not to rush too much. Okay. Either the wall side of the classroom, we've lost all the people from there. Were they sucked up out the windows and gone somewhere? I mean, no, they weren't here today. But those people aren't coming back. Okay. Anyone still writing? Okay. So, what do we conclude from some of this? The paleomagnetic patterns. Okay, let me go and get this here. And here we have I can't find you. Antonio, right? Yeah. Okay. Now remember, several slides ago, we had the magnetic fields alternating. Remember? Okay. And we said it has to be because of the Earth's magnetic field is alternated over time. Okay? The paleomagnetic, this is the ancient magnetic patterns of magnetic strips in the ocean floor basaltic rocks. Okay? Get all that down. Those are the iron-based rocks. These are where we find those alternating magnetic fields down there. They are identical magnetic reversal patterns on both sides of the ridge. Way out there, you have maybe 22 of those. Closer in, you may only have 15. Then closer in, but they're identical on both sides of the ridge. Fewer and fewer as you get closer in. Hey, those were once together, and they've been spread further and further apart. The patterns match those found elsewhere, providing age determination. So this is how they can come up with the 65 million years, 135, and 48 million. That's why, because they match other evidence of similar fossils and similar other issues that are going on. So this is what's happening. Now, I don't like this. To me, this is not quite a fair showing. They show only the growth being vertical, pushing out this way. What you need to have is also layering like this, because that's what creates the layers reversal patterns. Okay, they just show this as, but I get what they're getting at is pushing them further apart, but it's also depositing new material off to the side. And this would be on the older, this would be on the newer, and yet newer. And this is why the different layers. You get thicker layers here, and fewer layers as you go towards the center. But I get why they drew it that way. Okay? Lots of evidence here that's suggesting, wow, there's a lot of stuff going on. And this is Brandis, right?
You haven't taken the lab from Thursday, have you?
If people turn them in, I'll take them, yeah. So I'll take them anytime. In fact, some of them have been graded. And by the way, I don't know what you've done special, Asia, but you must have hacked somebody off awfully badly. Maybe because I did not activate any kind of a grade mechanism. But what you showed me the other day, you're the only one that's doing. And I don't know why. I can't tell any difference in how things. But what I've heard, everybody thinks this new blackboard is nuts. No one is trusting it at all.
It's messing up. I'm telling you.
Huh?
It's messing up. Our teacher, it keeps saying, our teacher, what it was saying, like something was due tonight. And it was like, it wasn't due, so she had to go back and fix it, and then still messing up, so she had to fix it again.
It's totally. We had a meeting with the dean and department chairs, and all right, good. Thank you so much. Got another moon lab in. Way to go. Okay. So don't trust anything that shows you. If it's a numerical grade, you can trust that. If it's giving you a letter grade, don't pay any attention to that because there's no rhyme or reason for it.
You're saying that grade's wrong on it?
I have, it's making up a grade. No, the number grades I put in, they're right.
So
Okay.
the letter grade?
The letter grade, I don't tell it to calculate it. It's doing it on its own, and it's not following any pattern that I can detect at all. And it just doesn't make any sense, yeah.
Are you going to get some of the test back?
I'm sorry?
Are you going to get some of the test back? Or
Okay. Now, we did have this question earlier, and let me repeat it. I hope everybody is paying attention to it. And in fact, this is a good time for a commercial break. Okay? Here is my commercial break. Out of this, one of the best classes I've ever had, how many research papers have I got in? None. Okay.
I'm going to start today. I think.
Okay. How many of my first labs am I missing? 1, 2, 3, 4. Okay. How many of my first tests am I missing? 1, 2, 3, 4. And they're not the same people, folks. Okay. How about my second lab? 1, 2. 2 people haven't turned in the second lab. Test 2. 1, 2, 3, 4, 5, 6. Lab 3, I've gotten a few in today. That's all I've had so far. Test 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Haven't turned in test 3. Unless, yeah.
What chapter was that?
That was the Earth Moon system.
Oh, yes.
16, chapter 16 test. Okay. Lab 4. I've only got 1, 2, 3, 4, 5, 6, 7 in out of 21 students. Okay? So, to answer Sholanda's question, as soon as I get all the labs or all the tests in, I return them to you. But while there's still some out, I can't return them to you. Otherwise, people will see the right answers. Could see one. What's that?
Yeah.
Oh, yeah.
They're all on Blackboard. All except things that have been turned in since Friday. Okay?
And you can come in between 10 any day of the week, except Friday, and take the test that you haven't taken.
Okay. Okay, let me answer that question. My office hours. The biggest bunches of office hours I have, Monday, 8 to 10 in the morning, and 3:45 to 6 in the evening. Okay? On Mondays. I have little periods in between. You can catch me in between classes, but that's about it. Tuesday and Thursday, 8 to 8:30 in the morning, and either right before or right after class. That's the best time to catch me on Tuesday and Thursday. Wednesday, 8 to 10 in the morning only. I don't have that evening because I have a physics class over on the Birmingham East Campus. I can't, as soon as I get out of my last class, I'm booking it to Birmingham.
Where's your office?
My office on this campus is down, you go down the half flight of stairs, almost to the end of the hall, last office on the left,
I see you.
across from the orientation classroom. Okay? And then Friday, 8 to 12 on the Birmingham West Campus.
I can come here and take the test also.
Second,
I can come here and take the test also.
Yeah,
Birmingham with you.
say that one more time.
He said, can you take the test also?
You can take the test over there, but you have to tell me on Thursday to put your test in my thing. Otherwise, it'll be here on Bessemer campus. Okay, so tell me Thursday if you're planning to take a test on Friday. And Jordan showed up. Jack showed up. Okay. All right. So right now we're only missing Brianna, Katie, and Shakaya. Okay. Good attendance today. All right. So did that answer your question? Okay. As soon as I get all of any lab or test in, I'll get them all back to you. But I can't return them until I get them in. Okay. All right. So, picking up where we left off, we had just been talking about magnetic C4 spreading evidence, and it's there. And it supports the idea of plate tectonics. The plates are moving, folks. Okay. All right.
Hey, we taking a commercial break.
Oh, do we need one? What time is it now?
3 o'clock.
3 o'clock. Yeah, that's not a bad time for a break. So let's take a break. We'll pick up here. Try to keep it less than stop and call roll again. Oh, I didn't turn on my projector. Sorry. All right, any questions so far, comments? Is this kind of making sense? It's pretty incredible stuff, sometimes almost hard to believe. Okay, just to get an idea of where we are now, we're on page 467, or at least in my book. It's the page that has example 18.3 at the bottom. And at the top of that right-hand column of 467 or whatever, there's this title, Lithosphere, Plates, and Boundaries. So that's what we're starting now. Okay. So these are the stuff we've been talking about is the basis or foundation for the whole concept of plate tectonics theory. Things we've been talking about form the basis for this plate tectonics theory. Okay? The lithosphere, which think of that as the rocky sphere, okay? The rocky sphere, lithosphere, broken into fairly rigid plates. Now notice they put weasel words in here, fairly rigid. There can be places in a plate that have weaknesses that may give or take a little bit, okay? So they're not totally rigid plates, but fairly rigid plates. The plates move ever so slowly, but they do move on the asthenosphere. Remember, it's sort of semi-liquid, elastic sphere there, okay? Your earthquakes, volcanoes, and other rapid changes in the Earth's crust occur most often, not always, but most often at the plate edges, okay? So this is where the action is, where those plates interact. There are three basic plate motions. One of these is diverging, meaning they're moving apart, like that mid-Atlantic ridge. Okay? There are converging plates. Because guess what? If those plates are diverging, does that mean the Earth's getting bigger? No. That means somewhere they have to bump into each other. And those are the converging plates. And then there are some places where the ridges are moving kind of parallel to each other. So those are called the transform boundaries. Three types of motion, diverging, converging, and transforming. Now here's a picture you saw at the very beginning, a little bit bigger picture of the major plates. Okay? Now, and again, when you take a globe and spread it out onto a flat piece of paper, the things at the top and bottom get blown way out of proportion because the equator, the circumference there, that's an exact measure, and these others get spread. So don't take, the Antarctic plate is not that big, okay? But it's centered around Antarctica, okay? You can't see the northern part too much. But here's the Eurasian plate, probably the biggest plate. Asia's the biggest continent, but not all of Asia is in the Eurasian plate. The vast majority, but not all, okay? And I doubt if it's a clean, straight boundary like this. It's probably pretty jagged, but they just don't know where the boundary is. My guess it would be up here along here, but wherever, okay? Now, North American plate's a pretty good sized plate. Not that North America's that big, but you got half the northern Atlantic Ocean in that plate. And then South America has half of the South Atlantic Ocean in that plate. African plate's pretty good size. And this is the interesting one, the Indian-Australian plate. Who would have thought that India and Australia are on the same plate and India is not on the Eurasian plate? Okay? This is Saudi Arabia mostly here, and that's called the Arabian plate. African plates here and here, and that includes part of the Atlantic Ocean, South Atlantic Ocean, and also goes way out into the Indian Ocean and somewhat into the southern part here. Now, the Pacific plate is a big plate, almost totally underwater, okay? There are islands in it, but that's a plate. Then there's some of the smaller plates. The Nazca plate here on the border of South America, the western side. And by the way, I'm going to tell you now, talk about a deep trench here. There's a trench. There's a trench here too, okay? Trenches up here and here. This is where the plates are, we'll get to that later, converging and trenching under each other. Philippines have a plate. That's a smaller plate, the Philippine plate. And here's the Caribbean plate here. And then there's a tiny little plate here called the Juan de Fuca plate. And that's up here just off the coast of Canada, British Columbia, Canada. I think that Victoria Island may be on that plate. I don't know for sure, but tiny little sliver of a plate there. Okay? These are all somewhat disconnected from each other, but they're right up against each other, so they make, and that's where, by and large, earthquakes, volcanoes, and other rapid changes happen. What do we call this area around the Pacific? It has a name, and Johnny Cash used it for one of his songs. The Ring of Fire. Okay, we have some Johnny Cash fans. Okay. That's where lots and lots of volcanic earthquake activity happens along that Ring of Fire. Okay? You also have a lot of earthquakes and stuff along here. Remember the tsunami that initiated in Indonesia? This was and went over into India and wiped out an awful lot of people on the beach there one Sunday afternoon. It was pretty horrendous. Activity up in Alaska here many years ago created probably the strongest earthquake ever recorded since we've been recording. Happened, and you can't see the Hawaiian Islands, but they're down in here somewhere. It sent a tsunami all the way to the Hawaiian Islands. That is a big tsunami. And that was back before it was well populated, so not letting any deaths. What's that?
Where's your Ring of Fire?
The Ring of Fire is basically the boundary around the Pacific Ocean. It's these plate boundaries that go around here. It's not too much down here, but mostly there. Okay. Now, let's start with the divergent boundaries. Divergent meaning moving apart. Let me go and get this slide up for you. It occurs between any two plates that are moving away from each other. And when they move away, that leaves an opening for magma to come up from the asthenosphere. Okay, now remember, this is just a general idea. This is your oceanic crust here. And these aren't drawn to scale, mostly basaltic rock. Here's the upper part of the mantle here, and that's the, this is the Mohorovic discontinuity here. This is the upper part of the mantle, and this is the place where the weakness is, and that splits. And this is the asthenosphere here, like I said, where much of the molten material will come from, and because you have a divergent plates here, that leaves a crack for that molten material to come up, the magma come up. and then it pours down the side. This is what makes it the ridge here, Mid-Atlantic Ridge, and it keeps pouring over the side. The lithosphere is everything above the asthenosphere, which is the upper mantle and the crust, whether it's oceanic crust or continental crust. The upper lithosphere and upper mantle and the crust, which makes up the lithosphere. Here is the asthenosphere, which is probably not this thick compared to that, but they've drawn it this way. And then below here somewhere, you have the lower part of the mantle that goes down to the outer core, which is liquid. Okay. So the molten material from the mantle, actually from the asthenosphere, well, but that's inside the mantle, rises to fill the fissures. Okay. New crust is formed as this volcanic material bubbles up here, and often accompanied with volcanic activity. If this comes and breaks the surface, that's volcanic activity. Mostly underwater, okay? We don't see it, we don't realize it, but mostly underwater. Like I said, that picture that they showed, absolutely phenomenal to see that stuff just bubbling up and turning right into rock because the water down there is so cold, okay? Often accompanied with volcanic activity. The prime example of the Mid-Atlantic Ridge. That's the biggest continuous divergent boundary I think we have on the planet. There are other ridges, and we'll see that in the last chapter we do when we're studying the oceans. We'll look at those. Then we have convergent boundaries. Okay? This is where, if those are spreading apart, somewhere they have to be crashing into each other. So this is the other side of that coin. Convergent boundaries. These occur when two plates are moved toward each other. Okay. When this happens, the old crust, and part of the mantle too, has to be destroyed. Okay? And we'll talk about that in just a little bit too. That creates what they call a subduction zone, at least in two of these. In the third one, you don't have subduction zone, but in two of the three, you do. We'll get to those in a minute. And this is a belt where one crust has to go under the other crust. Okay? The subducted material moves under. There's a lot of friction there. A lot of heat is produced. Some of it is melted and partially melts and then joins the mantle, solidifies in the mantle. Other finds crevices when it melts and comes up as volcanic activity. So there's another thing that's happening. Or some of it subducts so far it then joins the asthenosphere. Maybe going down to the core, I doubt it. I think it just goes into the asthenosphere. And that's where it keeps replenishing itself. What it loses coming up in the divergent boundary, it's gaining by the subduction. So here are the three possibilities for convergent boundaries. What if you have one continental crust, crust hitting an oceanic crust or oceanic plate? Okay? What's happening there? Which of these is denser? Oceanic or continental? Oceanic. Which is thicker? The continental. So here's what's happening. The denser oceanic, dense oceanic, subducts under the thick, less dense continental. So you have oceanic going under continental. That's what makes those trenches, because that the floor of the ocean actually goes underneath the continent. Okay? Now remember that figure I said I didn't like because it showed the oceanic trench climbing up? No, it's going down underneath. Okay, so that's the first. We're going to look at these individually, so don't sweat it. Then you have converging oceanic plates. two oceanic plates coming together. And always one subducts under the other. I don't know who determines who wins or loses on that one, but maybe one's a little denser than the other. It just got started that way. I don't know. But then the third one, converging continental plates. Whoa, neither one of those is going to subduct, so they grow. They crash into each other and move upward. So the subduction zones occur in these two cases. There isn't a subduction zone in that one. Okay? So let's look at these individually, these three possibilities. First, the ocean continental plate convergence. The ocean plate is a denser, let me go and get the thing up before you take the picture. The ocean plate is a denser basaltic material subducted under. See, this is what's happening. The ocean plate goes under. It doesn't crawl up that way. It just doesn't happen. It goes under the less dense granite-type continental shelf. Now they're introducing that term here. We'll see that again in a later chapter. Okay? This is what's occurring. Now, when that occurs, this is not a happy picture. Okay? Because this is a rough, hard, dense material crashing under another hard material. And that creates an enormous amount of friction. And when that friction occurs, some of this actually melts, and then you have volcanic material activity, not out in the ocean, inland, because this is going underneath the continental shelf. And when it gets really hot down here, or the other thing, if this extends all the way to the asthenosphere, this creates a crevice or a crease that stuff can come up from there. So wherever it comes from, the magma comes up into, and this is what forms part of that ring of fire around the Pacific Ocean. Okay? That's why, let me get my visual aid. Something really nice about this map is got some topological characteristic to it. If you feel along here, you feel mountain range. All along here, especially South America. Wow, the Andes here, tall mountains. Volcanic mountains because of subduction underneath. Now the Nazca plate is right in here, and the Pacific plate is other places here, and this has created some very tall volcanic mountains, yes.
So the Himalayas are formed the same way?
Not quite. We're going to get to that later, and that is an important thing. They're not volcanic. These are volcanic. You go up here in the Cascades and the Sierra Nevadas here, you have lots of volcanoes. There's Crater Lake somewhere in there. There's Mount Rainier right outside Seattle. Okay, possibly. I don't know that one. Mount St. Helens is right in this area near Portland. You know, there's just all these volcanic mountains. And up here in Alaska, that major volcanic activity that created tsunamic waves all the way down to Hawaii, if I can find there's Hawaii, covering a huge portion of the globe there. Major tsunami way back then. Over here, Japan is an island chain, volcanic islands. That's why it has no fossil fuels to speak of. Well, it hasn't been there that long, okay? You have mountain ranges here. You have mountain ranges here. You have mountain ranges you can feel. Now, here's the Himalayas here. We'll talk about that later. Not the same story, okay? Here on the west coast of Australia, mountain range. New Zealand, they don't feel much here, but yeah. That's why you have all that activity there. The ring of fire, okay? Now, and this is where it comes from. That subduction of oceanic plate underneath the continental plate. Okay. So you have these deep, deep trenches here. Like I said, when you go out of San Francisco Bay, the the bottom just falls out and then comes back up again. You know, that trench right along the edge of the continent there. Okay. You have deep-seated earthquakes. We'll talk about what that means later. That's another chapter. And then the volcanic mountains right along the edges. And the example of this is the convergence of the South American plate with the Nazca plate. That's for the, I was pointing out right here, right in here, really tall Andes mountain range here. Basically, the whole nation of Peru, Chile here. Peru is right up here, okay? And it's pretty much that too, but Chile is just about all mountain range, okay, right there. Okay, and they've had some pretty major earthquakes and volcanic activity in Chile as well. Now, the ocean-ocean convergence. Did anyone need that last one longer? I didn't think to ask before I changed. I thought I'd done enough talking. Okay, here, now you have two basaltic plates, both of them high density. I don't know what's got it started, but whichever one started going down, it started going down too. So the oceanic crust here subducts under other oceanic crust. Okay? Now what forms here? These form those arc islands. Okay? And you will see this all. And deep trenches here. Okay? Showed about the same as before. These are even deeper. They just reduce the scale here. Same type activity here. That is not a happy situation here. This crust moving under there, the grinding, the heat, the stuff it creates, it melts rock, and that creates volcanic activity. Also provides seams for the asthenosphere magma to creep its way up here and get to here. Now, if you look at that, certainly Iceland, remember, that was from diverging plates. That's where that came from. But in the Pacific, look at all these chains. Japan, arc islands. Aleutian Islands, arc islands. Much of Indonesia, huge arc of islands. And also Papua New Guinea, New Zealand, arc islands. And then you just come out everywhere. The Kiribati Islands, the Line Islands, the Hawaiian Islands. These are all arcs of islands. Caroline Islands, the Northern Marianas Islands. Now hang on to that. Northern Marianas Islands. Why did I want to mention that? Anyone know? The trench along this, I don't know which side it's on, is the Marianas Trench, the deepest part of the ocean period, where one oceanic crust is subducted under the other. So that creates the deepest trench known in the ocean. So there's all these, they form these island arcs. Okay? That's where one oceanic crust subducts under another. Associated with deep-seated volcanoes, they mentioned shallow earthquakes here, but deep-seated earthquakes here and volcanoes. The island arcs, that's what I was just talking about, form where the melted, subducted material rises above the sea level. Now what you don't realize is all along here you have other mountains that have just not reached the surface yet. Okay? They're called submarine mountains or submarine volcanoes. And you have them. And when they finally grow above the surface, that's when we see the islands. And Hawaiian Islands are some of those. These island arcs form where melted, subducted material rises up above sea level and through the overriding plate, and then you have new landforms forming. Okay? Ocean plate convergence. And then the continent plate convergence. Here, less dense granite and less dense granite come together. Hey, nothing to subduct here. Number one, continental plates are really thick. That would be really hard to subduct. But number two, they're about the same density. So they just crash into each other and rise. Okay? The colliding plates pile up. If you're wanting to get pictures, I should have done this one. Okay, pile up, producing a deformed, thicker crust of lighter materials. And here, this example, the Tibetan Plateau and the Himalayan mountains. Because guess what? India is not part of the Eurasian plate. It's part of the Australian plate, Indians, Australian plate. And this plate is crashing into the Eurasian plate. And that's why the Himalayan mountains are growing. They are growing. They're getting taller. Tallest mountains in the world, still getting taller. Not very fast, but they are. And the Tibetan Plateau is all in here, where it's been lifted up. Okay? Now, not just there. The oceanic continental plate conversion here also raises up things. In fact, my wife and I saw this when we were out west near Yellowstone, but it's not in Yellowstone. Out here we were driving along and we found, and it's mentioned in the book somewhere, coming up pretty soon, basalts up here in high elevation. What's happened? It used to be ocean floor, it's been raised and raised. So it's pretty far up there, okay? So you have basalts where you wouldn't expect basalts. But here's the Himalayan mountains. That's exactly what's happened with them. Okay? I'm guessing the Tetons are sort of like that too. So it's not plates, it's weaknesses in the plates.
So I guess the Rocky Mountains form differently.
Say again?
I guess the Rockies form differently.
Yeah, well, you see, the Rockies were formed by the ocean continental convergent and built that way. But it's well inland, so there is some of this crashing together, but it's been forced by the motion out here that made them rise. Yeah, it's very similar to this, but it's not too different. Continental plates. What's that?
What time we have a break today?
I thought we just did. What time is it now? 3:30? Want to break at 3:45? Is that going to be all right, or you rather break now? 3:45 is all right? Okay, because I got a call rolled in anyway. We might as well break. Okay. Now, yes. Go back. This, okay.
So what about the Appalachians?
Appalachians are interesting. They are actually mountain ranges that are getting smaller. They're eroding away. There is some thought that at one time the Appalachians were the tallest mountains in the world. But over time, they've eroded away and filled in the valleys, and they are now actually getting smaller. If you look at the Appalachians, most of them are rounded, meaning erosion has occurred. Look at the Rockies, and they're jagged. That means they're still growing. Himalayas, jagged, still growing. Appalachians, rounded. I think the Ozarks are probably rounded. I don't think they're growing much anymore. Alps, still growing, jagged. Okay. So you can tell a lot about mountains just by looking at their shapes. Okay. Now let's move to transform boundaries. So what are 3 types of boundaries?
Oh, 3 types of boundaries.
Divergent, convergent, and transform. Yeah, transform is when they move past. These occur when 2 plates, I don't like this verb here, they don't slide, okay? They resist like crazy, okay? They move past each other. They grind past each other. I wouldn't say they slide past each other, okay?
You said there's 3 types of
boundaries. There's divergent boundaries, convergent boundaries, and transform boundaries. Divergent moving apart, convergent moving together, transform moving past each other. The crust is neither created nor destroyed in the process. So in the divergent boundaries, new crust is being created. Convergent boundaries, generally it's being destroyed. Transform boundary, new crust is neither created nor destroyed. Now, what the problem is, this is why I don't like the verb slide, there are irregularities in the movement along the boundaries, okay? Sometimes they may move without too much problem, not normally, but when they do hit snags, the pressure builds, and then suddenly something breaks or releases. That's when you have earthquakes. Okay, the sudden jerks, those are not guys, okay, produce the earthquakes. Okay? Guess where some of these are? San Andreas Fault along the California coastline. If you think about the major earthquakes we've had in the U.S., in my lifetime, and perhaps some of yours, before my lifetime, there was a major earthquake in San Francisco right around 1900 or so. That's before I was born. Okay? Do you remember there was a World Series? The San Francisco Giants were playing the Oakland Athletics. Remember that one? And what happened? There was an earthquake right in the middle of the World Series. Now, not while the game went on, I don't think. Oh, it was while the game was going on. And there.
It was in the 80s, right?
Second?
It was in the 80s.
80s, I think, yeah. There is, oops, I went to the wrong place. There's down here in the San Francisco Bay, you can't see it on this map, there is a major connection between San Francisco and Oakland called the Bay Bridge Tunnel. Okay? Now, Golden Gate Bridge is out here along the coast, but this is across the bay. Now, it's called the Bridge Tunnel because it was a bridge between Oakland and Yorba Buena Island, then tunneled through Yorba Buena Island, and then a bridge over to San Francisco. Okay? So it's called the Bay Bridge Tunnel. It was about rush hour, I believe, and the Bay Bridge Tunnel was packed with people. One lane, I can't remember which, eastbound on top and westbound on bottom, or one way or another, but you know, traffic going this way on one, this way on the other, on top of each other. I think there was actually railroad tracks underneath them too, Bob. I can't remember that for sure. But there were two layers. When that earthquake happened, some of the Bay Bridge Tunnel collapsed on cars underneath. Not good for the people up here, and really not good for the people down here. Lots of deaths from that. Okay. Along the San Andreas Fault. Within a fairly short time, I think a year or two, they had another quake down in the Los Angeles area. And there it wasn't quite as bad, but it was still pretty bad. A lot of the expressways went over streets, just like they do in downtown Birmingham, down on top of streets too. So, not a good thing. All along the San Andreas Fault, along California's coastline. Okay? Transform boundaries. Now, in a later chapter, you're going to see a picture along the San Andreas Fault. It's not in this chapter, it's in one coming up, I think 2 or 3 chapters from now. Okay? Unbelievable picture. Just incredible. Hang on for that. Now, what are the present day understandings? Basically, we don't know. Okay? We make guesses. The major remaining question, what makes the plates move? Okay? Why is this happening? Now, there's several current working hypotheses. Okay, one of these is you have these convective cells in the asthenosphere. Remember, the asthenosphere is semi-liquid, which means there's molten rock there. Well, picture when you're boiling a pot on the stove. Right over the eye, the water's moving up, and along the edges it moves back down. So that's convection. Okay? Hot material rises, cooler material sinks because of changes in density. When it heats up, molecules move further apart, less dense, it rises, and then when they cools, they get closer together and sink. That's convective, okay? So the convective cells in the ionosphere. Hot fluid materials rise at the diverging boundary. Some escape to form new crust, but others get pushed out and spread beneath the lithosphere, dragging with it the overlying plates. So that's one, okay? What's the problem with that? Where's the evidence? Why are the convective currents there? We don't know, okay? Now there's a couple of others that are kind of mixed in here, and they have a couple of weird names. I think it was the older books that had them in it, older editions. Here is an interesting example. I'm sorry, I should have done this a while back. If the distance between Natal on the eastern point of Brazil, okay, and Mount Cameroon in the western Africa is about 5,000 kilometers. Okay, now where we're talking there is, this is back on the plate movement. There's Natal right there, and in eastern Brazil, and Mount Cameroon is right there. That looks like about where that would fit, right? If these are pushed together. If that's about 5,000 kilometers apart, they're saying, how long would it take if the plates are moving at about 2.5 centimeters per year? Now, 2.5 centimeters is just about an inch. 1 inch a year. If they're about 5,000 miles, it's just a math problem. It would be 200 million years, okay? And that's nothing in geologic time, so who knows? Okay. Now, before we move on, this is a good follow-up. Oh, wait. If the distance between Porto de Cedra and the southeastern coast of Argentina and Cape Town in South Africa, okay, again, they're about 6,900 kilometers apart. How long did it take the southern Atlantic Ocean to open if its average rate of spreading was 3.25 centimeters per year? It would be about an inch and a half. That would be about 2.12 times 10 to the 8th. Well, that's about the same. One was 200 times 10 to the 6th, and this is 212 times 10 to the 6th. So that's about the same. They just put their decimals in different places. Now, how do we know that? 1 inch a year or something like that? Measuring plate movements, okay? The very first human lunar landing took place in July of 1969. Astronaut Neil Armstrong stepped onto the lunar surface, blah, blah, blah. You know all about that. What they did, they placed a number of experiments on the lunar surface in the Sea of Tranquility, is called there, and some of those were reflecting objects that they could measure from Earth. You know, send up, say, a laser and beam it back, and they are able to measure plate movements using the moon as our standard, you might say. So, well worth a read. Closer look, measuring plate movement. Okay? They have some more examples here, which some of them they're just exercises in doing math that have no real direct bearing to what we've been doing, so I'm going to skip those. All right, present day understandings. Here's a mistake and misunderstanding. Is there a chance that California is going to break off and fall into the ocean?
Yes.
People have said that. Hey, that's a transform boundary. It's not a thing. Earthquakes don't happen that way. Earthquakes don't open up and people fall in and buses fall in. That's science fiction. Mostly fiction, not science, okay? That's Hollywood. So, no, California's not going to break off. If anything, California's going to shift a little, but those are transform boundaries. The earthquakes are happening, but it's not opening up. It's moving past each other like this. We'll see the picture in a later chapter. Okay. This is the picture on page 471 of what we're talking about here, pretty close to it. And this is the source for the just inside volcanic activity is because the plate sliding past here, I say sliding, not sliding, moving past here, grinding past here, heating up, creating magma as it goes, and then that makes its way to the surface. It is, okay. Same thing over here in the island arcs. The places where the subduction of ocean subduction happens, that forms the island arc nations that are basically boundaries here. You don't have these in the same ocean, they just put it all here. This is the spreading here, subduction there. New landform created here, old being destroyed there, or joining the mantle there. Okay. All right, let's call roll, and we'll take a break after that. Okay. In fact, I'll go on and pause the recording now. No reason to. Any questions on anything we've done so far? All right. Now, there is in the book on page 472, at least in my book, I don't know what the page numberation is in yours, but it's a picture of people behind the science. Henry Hammond Hess, a good alliterative name. He was a naval officer who, and if you think about what happened in the Navy in the time he was alive, 1906 to 1969, he only lived 63 years, but in that time we had World War I and World War II. I can't talk. And Korean War and several others. But he was a researcher, naval research. He was a U.S. geologist who played a key part in the plate tectonics revolution in the 1960s, and he died at the end of that decade. First studied electrical engineering. I won't read it all, but you talk about studying the cores, the plate movement, and stuff like this. He was on top of it. I bet you he mapped so much of the ocean floor by sonar and other things like this. He was right in there, okay? Now, just below his blurb was, and he's a good paper topic if someone is interested in that type of thing. There are some other names mentioned here. One of these is D.H. Matthews and his student F.J. Vine, and they did some of the work within it, so there's lots of potential things. Remember, this can be a source for ideas for the paper, but it can't be your source for the paper. You have to get your sources outside the book. All right. Then there's another figure that looks sort of like this one, but they don't show it in the slide set. And that's on page 472 as well. And it shows a couple of the other theories. We mentioned one, the convective cells in the asthenosphere that goes up and pushes apart. Another is what they call the ridge push, that the ridge is up here pushing downward on that slanted asthenosphere, so that's pushing. The other is the slab pull. So here would be the ridge pushing down because you're always building new rock here, and that's pushing down on the existing one. So that could be part of the primary mover. Or where the plates are subducted here, they're pulling down here, and they call that slab pull, pulling it that way. It could be some combination of all three. Who knows? Okay? So, And I sure hate it when they use verbs like slide. The plate slides downhill on this surface. It doesn't slide, it grinds downhill on that surface. Now there's another Science and Society here on geothermal energy. We talked about, well, no, maybe we didn't. That was another class. There are certain places where there is lots of geothermal energy fairly near the surface, and the Juan de Fuca plate, that little bitty sliver of a plate up there off the coast of Canada, but also part of that touches us, and there's some source for geothermal energy. Hawaii has geothermal resources. There are power plants in California on 10 sites, Hawaii, Nevada on 10 sites, Oregon and Utah 2 sites. So we need to take advantage of those as much as possible, because it's clean energy, it's existing energy. We don't have to do a thing to burn to get it. And I think Eric just came back, right? And at the same time, it looks like we lost a few. Okay. So geothermal energy could be a really good paper topic, or something coming off of that. Okay. So the first figure I showed that was like that is the ridge push. On the next page, 474, is the slab pull. Frankly, this one shows both of them to some extent. Okay, there's new earthquakes and volcanoes. You can certainly read that. Just a little concept supply. And as I say at the end of every chapter, nothing replaces reading the chapter. Okay? Now, this chapter has one of the shortest summaries I've seen, so boy, I think it's even more important to read the chapter here. The key terms, again, a fairly short list here, so really important to read the chapter. Even though they're listed alphabetically, they give page numbers for their first location. Applying the concepts, though, 52 questions here, which is more than normal. So that's a lot of good resources for studying for your test. The answers are given. Do that. Now, you're going to see this later, so I'm going to go on and tell you now. On page 478, or at least in my book, questions for fault. If everybody's got your book, see those on page, and there's 16 of those. Then for further analysis, there's 4 of them. Okay? That's a total of 20 questions there. When we do the lab is only going to account for, it seems like, 10 points worth. I think that's about right. And then you've got to come up with another 15 points. The 15 points comes out of those 20 questions. 15 or more questions out of those. Well, the reason I say or more, what if you miss something somewhere else? If you do a few extras, then if you get a total of 25 points, you get 25 points. If you don't do but 25 and you miss a couple, that only may be 23 points or something like that. So I would say do several. A great thing to do before you take your test on this chapter. So I would try to get this part of the lab done. You can go on and get started on that if you wanted to. So I guess that's a good point. Oh, and then you have invitation to an inquiry measuring plate motion. We talked about some of that before. And then the parallel exercises, group A and B, basically are like the examples, which are kind of made up. Okay, so, question. It's now what time? 4 what? 4 o'clock, basically. Okay? Now, we're going to stop at 5:15 for you to take your chapter 17 test. Okay, the 2 options now. Number 1, do the lab for chapter 18, which the lab itself is pretty short. The questions are the bulk of it, and those can be done at home. Or go on and start chapter 19, and then on Thursday we'll do the first 2 hours of 19, and then the next 2 hours of the lab for 18, and then 30 minutes for the test on 18. Because we did finish the chapter today, so the test for 18 will be Thursday. Okay, so which would you rather do? Lab now? Okay. So what we'll do is, let me go on and get out of this. All right, folks, sorry I forgot to turn on the recorder. What do we get the density of, well, wait, what do we get the mass of the salt to be?
162.
162 grams. What do we get the volume to be?
56 cubes.
56 cubic centimeters, is that right? Okay. And what did you calculate the density to be?
2.89.
2.89 grams per cubic centimeter. Okay. Now we're going to measure the mass of the granite. So, did you zero the scale?
Yes.
Okay, good. Put it on. All right. What do you get as the mass?
I don't know how to read this. So,
Okay.
do I read the 40 or the 450?
Like 440.
Huh?
400 something.
Yeah, 450. 450.
And then any past that? Each little block line is a gram.
41.
Say again?
But it's a little bit over 40. So 40.
Oh, okay. 441. That's what you're saying?
441?
Yeah.
441 grams.
Mm-hmm.
Okay? Someone else? Come and let's very carefully, slowly lower that into the water. Because we're still packed at the very top. Did you do something before? Oh, you didn't? Okay. Hold it by one corner. One corner. Okay, I'll do the small one from this end. Yeah, like that. Hold it by one corner. Okay. Very slowly lower it into the container. Very slowly lower it. Catching the water as it goes, slow so it doesn't splatter. Keep lowering, keep lowering, keep lowering, keep lowering. Now that piece of the salt that's on the edge, see if you can get it to flip over and go down. There we go. Did it? Keep going. Keep going. There we go. It all went in. Okay? Now, someone needs to take that. Oh, dump that water out, somebody. Someone who hasn't done something. Need some help up here. Okay. Dump that water out of the graduated cylinder. You can pour it back into here. Okay. Take this water and dump into there. Okay, it looks like we may have splattered a little, but we'll see. Okay, go ahead. You did well. Okay, now somebody pour that into the graduated cylinder. See, that has a good spout. Okay. Someone needs to measure the volume here. $185? $195?
No. Yeah.
Yeah, okay.
No,
Okay. That's 190 right there. So is it much above? Oh, 190. 190 on the nose?
Yeah.
Okay, didn't know it has a nose, but okay, 190. All right, that's the volume in cubic centimeters. And then divide the mass by the volume. Say it again. 2 point or 3 point? 2.32? Okay. Everybody get that?
Yes.
All right. Now, which did you think was going to be denser, the granite or the salt? It was a big piece of granite. But guess what? Its density was less. Is that what we expected?
No.
Wait a minute.
There was more
Wow.
pieces of the
Huh?
Oh, there's more pieces of salt.
Because it was bigger and heavier, but it also displaced more water. So its density, the ratio, is less. Okay? Now, if someone's got a book, if you bring me the book, I can save a little time, because if I release this, it's going to spill, I'm afraid. Let me see if it does. Yep. Now we'll see if it stands. Yeah. No one tilt that. Okay. If you turn in your book to, we saw it in class today. So let me see if I can find it. There's a table up in the upper left of one of the pages. There it is. So my page 461 is the page with the globe with the inner core, outer core, mantle, and crust. You see that? It's table 18.1. On the same page is figure 18.3 and 18.4. Okay, look at that and see what the density of the oceanic crust. What does it say?
3 grams.
3 grams. We got the salt. 2.89, not too far off. The continental crust, 2.70, 2.7. What do we get? Say again? 2.32. So ours was a little bit lighter. I was expecting it to be denser, but we did maybe have a little measurement error, but not much. So you see, we were right in the same ballpark here, that the continental crust, granite, is lower density than the oceanic crust, which is our basalt. So that makes it feel nice, warm, and fuzzy inside, doesn't it? All right. Now, I think that we finished 1 through 6 of the procedure. You filled in the table, right?
Yes.
Okay. Now, results on page 336, number 1. We are recording, right? Number 1. In what ways do igneous rocks have different properties? We answered some of these questions earlier. In what ways do igneous rocks have different properties? What's it called? Color is one, for sure. Other different properties? Say again? Density, for sure. We just measured those. Okay. Material content, chemical content, something like that. That's certainly different. Any others?
How they fit, like the coarse and fine.
Coarse and fines. That would be texture. The textures would be different. You want to think of any others? That sounds like you got the major ones. Okay? Say again?
I was going to say the prices on along with that 4.
Okay, yeah, we're going to get to that. Okay? Number 2, explain the theoretical processes, this I think what you were just talking about, are processes responsible for producing the different properties of igneous rock. So what's the first one you said? Color. Right? Is that the first one you said?
Yes.
What was the different theoretical process or processes would contribute to that? The different elements that make it up.
Yeah.
Okay? So color would be the different elements that make it up.
How about streak also?
Say again?
Streak.
I can't hear.
Streak.
Streak. Okay? We didn't do streak with these, so let's leave that one alone. So, but color will be fine. That's good. What was the second one you named? Density. What would contribute to the different densities? Someone mentioned it earlier. Iron content. Okay, that would certainly be one. The iron content. And that also contributes to the color as well. Yes?
So color will contribute to what?
Say that again.
So color.
Color, the mineral content. Elemental content, something like that. What materials make up that rock? Okay, what's the next property we listed?
Material or chemical content.
Okay, material or chemical content. We've sort of been using that down in number 2 as well, but you remember Bowen's demonstration or thing that we had? It was what comes out of solution earliest. The high iron content comes out very early at very high temperatures, and the lower iron content, like the granite, comes out at cooler temperatures. So when the molten material, all igneous rock came from molten rock, okay? So when did it come out of solution and become rock? At higher temperatures, you have the higher iron content, lower temperatures, more silica content. So that would be what determined the temperature at which it hardened. Okay? And what was the last one? Or was that the last one? Say again?
Texture.
Texture. What theoretical process or processes are responsible for producing different textures in the igneous rock? How the rate at which it cooled. Absolutely. Y'all were paying a lot of attention to that chapter. Huh? The rate at which it cooled. You said that earlier, I thought. Okay. Number 3. According to the experimental evidence of this investigation, propose an explanation for the observation that the bulk of the Earth's continents are granite and that basalt is mostly found in the Earth's interior. What do we find out the difference between granite and basalt?
The salt was in the ocean.
The salt was denser,
Yeah.
so therefore it would settle out deeper, and the less dense granite would settle out higher. So that would do it, wouldn't it? An explanation for the observation: the bulk of the Earth's continents are granite; they're up on top, and the basalt is found in the interior. Second? I can't hear you. Okay? Because we found out that the basalts were denser than granites, right? That's what we found out in our experimental investigation. Okay? So therefore, you would think the denser materials would settle out lower into the interior, and the less dense granite would rise to the exterior. Don't you think? Now, in order to cut down on some of the questions you might have to answer, and won't do it by much, but a little bit, here is that piece of pretty heavy feeling rock here that we're not sure what it is. Some people think it might be meteorite. Other people think it might be just some sort of iron. It feels pretty heavy. You want to do the density of this. It may not, it probably is igneous, but we don't know that for sure. We know granite and basalt is. We think this probably is. You want to do the same thing for this one? Just to see? Okay.
We won't have to answer as many questions.
Uh-oh. I don't think we can do this one. Our scale won't measure it. Sorry. I thought we did it one time. It's too heavy. Let me see if I got another scale.
Well, 500. I think 450. 500.
Let me see if it will work on this one. This goes a little bit heavier. Okay, we first got to zero this one. Okay, does that appear to be zero?
Yeah.
Okay? Seems pretty close to zero to me, right?
Yeah.
So let's put this on and see what we can do. This goes up to 500 there. This goes up an extra 100 there. And this only goes an extra 10. Nope. 610 is more than that. Sorry.
You have a different route.
What's that?
You have a smaller rock.
No, that's. Anyone want to break this for me? Okay, never mind. Okay. All right. Wish we could have, but we can't. So we ain't. Okay. All right. How are we doing on time? Okay, did I tell you number 4, you answer however you want to, but you be sure to answer it, right? Okay, so you see that only gave us 6 and 4, 10 questions. We need 15 more points to get 25. That's where the questions come into play. And y'all are working on those, right? And the time is now 4:53. So
Can we turn this the questions in on explain?
okay, we started at 5:15, so I'd say work on questions until then. But if you need to leave early and want to take the test early, you can. Now, what was your question, though? No, ask your question. Yes, please. No, I want to hear your question. We're losing time. Go on.
Can we finish this at home?
Huh?
I said, can we finish?
Oh, certainly you can. Okay, now, let me say this about that. Remember, the Chapter 18 test is the last 30 minutes on Thursday. I would highly recommend you get those questions answered before Thursday. You don't have to, but that is a great study tool for your test on Thursday, is to do that. So be sure you, huh? What's that? Okay, I hear people asking questions, but I can't make out what they are.
Yeah, but I'm just like, this coming Thursday, like.
Is the test this Thursday?
Yes. Remember, this is a mini-term course, and we're covering 9 chapters in in 8 weeks. So, yeah, it's come pretty fast and furious.
How many have we covered already?
This will be test 6, 4 to
3 to 4.
yeah, test.
Thursday we did it.
Yeah, Yeah, that'll be the 5th. So we're about halfway there. And we're at midterm. Midterm of the mini-term. Yeah.
Six.
You can take the test.
You can take the test now if you'd like to.
I need to get them.
Huh?
Yes.
You want it now? Okay. Any questions before I turn off the recorder? Everybody understand everything you need to do with the lab? Okay? Now, somebody has already turned in the lab, that's fine, but remember to, if you don't turn in the questions, this can only be 10 out of 25, okay? Turn in the questions and you, of course, get more than that, so.
So we gotta do the questions.
So we gonna turn
them in together.
You don't, you can turn them in separately or together. If you're writing the questions on here, which there's not much room, but if you're writing on a different piece of paper, that's perfectly fine. Okay? So,
Invitation inquiry. What is that?
but you see, it is a lab, and y'all can work together on the questions if you want to, but you can do that at home or whatever too. But, okay, remember you don't have to turn in the lab by Thursday, but I would definitely try to get those questions done by Thursday just as a help for study. Okay? So, any other questions before I turn off the recorder? Okay, any questions? Okay. I'm going to shut it down.